All right, everybody. So now that we have talked about the different pressures within the respiratory system, I'd like to introduce you guys to the ideal gas laws, because in order for us to better understand how the respiratory system actually works, we really need to better understand what have gone on now to become what we call gas laws. And the scientists that have developed the gas laws have based them on concepts of what we call ideal gases. And ideal gases are just gases whose molecules are so far apart that they typically don't actually bump into each other. And the gas laws are also created based on the premise that gas molecules themselves do collide with the wall of their containers and therefore do produce forces called pressure. And there are various different things that can affect pressure, and each of those things are described within one of the gas laws. So, for example, Boyle's law is going to discuss how the volume of a container can actually affect pressure. Charles's law describes how temperature affects pressure. Dalton's law describes how the relative amount of different gases in a mixture will affect pressure. And then finally, Henry's law discusses the solubility of gases and how they affect pressure. So I'm going to go through each of those laws here in this little video. So we're going to go ahead and start with the first ideal gas law of Boyle's law. Boyle's law is, again, as I mentioned before, going to describe the relationship between pressure and the volume of the container that a gas is placed in. And so Boyle's law states that a gas's volume is inversely proportional to its pressure. And the really important words here to pay attention to are inversely proportional. So inversely proportional. Very important words here to highlight, because what that means is that if one thing increases, the other will decrease. And we have actually talked about Boyle's law before, but I've never actually told you that this is the name of the law that we're describing. So if we look at our first situation here, at constant temperature, we have a pretty large volume of space. And what we can see is that the gas molecules inside of here are actually spread out pretty far from one another. And therefore, the pressure here, noted by the pressure gauge, is actually pretty low. Okay. And so if we have a large container, a high volume, increased volume, that means that we're going to end up having a low pressure. That's different from this scenario to its right, in which we push this little piston and now we have decreased the volume of our container. Okay. And when you decrease the volume of the container, what you're doing is you're forcing the gas molecules inside of that container to be now closer to one another. And when molecules end up getting closer to each other, they bounce off of each other more frequently and they bounce off the walls of the container more frequently. And ultimately, that leads to an increase in pressure. Okay. And we have applied this scenario to ventilation in that when you think about what's going on with ventilation, when you inhale, okay, and this is, again, remember, inhalation is active, and that the diaphragm contracts. And so when the diaphragm contracts, that actually makes the thoracic cavity larger. All right. And so when you're making the thoracic cavity larger, that means that the pressure that's inside of the lungs is going to be dropping. It's going to drop so much so that it actually ends up being lower than the pressure in the outside world. And therefore, things are going to flow down their pressure gradient from outside, where it's higher pressure than what is currently in the lungs inside. Right. And that's actually why we move air from outside to inside. And the same is true for exhalation, but sort of reversed, because during exhalation, the volume of the thoracic cavity starts becoming smaller. And it's going to be kind of like this situation over here, in that when the volume starts getting smaller, the air that is actually built up inside of the lungs starts getting closer and closer to each other, starts interacting more frequently. So that increases pressure. And when the pressure inside of the lungs becomes higher than what the pressure in the atmosphere is, that's when air decides it's going to move out of a high pressure environment within the lungs to the outside world. Okay, so that's just a short little description about Boyle's law. The next thing I want to discuss is Charles' law. And Charles' law is talking about how volume is going to be directly proportional to temperature if we hold pressure constant. Okay, and so if I just wanted to think about this for a second, Boyle's law, I'm just going to write it up here in the top left corner here. Boyle's law said that we had a constant temperature and we had changing volume and pressure. Okay, but in Charles' law, we're actually saying something a little bit different. We're saying that in this scenario, we are going to hold our pressure constant, and therefore the volume and the temperature is going to change, and they are directly proportional to one another. Okay, and so what that means in terms of Charles' law is basically that it's saying, it's sort of right here in this equation, that if something is directly proportional, we're saying that if the volume increases, the temperature of the gas is also going to increase. Okay, and if the volume decreases, the temperature of the gas is also going to decrease. Okay, and that is at constant pressure. Okay, so another way of saying this is that pressure is proportional to temperature when volume is held constant. And so from this equation, or from this law, really what we gather is that during inspiration, okay, when we breathe in, air is actually going to expand in volume as it's warm by the respiratory mucosa, because what we're saying at this point is that we're increasing temperature. The respiratory mucosa are going to cause an increase in temperature of the air. And Charles' law says that if you increase temperature, that means you're also going to increase the volume of the gas itself. All right. And therefore, we're saying that air is actually going to expand as it becomes warmer. Okay. Hopefully that makes sense. Let's go ahead and move on to the next law, which is Dalton's law. And Dalton's law is dealing with the idea of what are called partial pressures. Okay, and so if we look at, let's just say atmospheric pressure. Okay, we've talked about this one before. Atmospheric pressure, and let's say it's 760 because that's what I have told you it is, and that's what it is at sea level. So let's just think about that for a second. Okay, so here is our atmospheric air right here. And what we should know about our atmosphere is that it's made up of various different gases. Okay, so the gases that are in our atmosphere are things like nitrogen, things like oxygen. There is a little bit of CO2. And so the combination of these different gases ultimately gives rise to the total pressure. All right, so let me erase some of this stuff for a second. And let's look at this in context. So here in this first box, again, we're going to say this is the atmosphere air. All right. And we can see various different colors. We can see various different colors within this box. Okay. And we're going to then say that this first box represents the pressure that nitrogen attributes to the atmosphere. This second, we'll say, is the pressure that oxygen contributes to the atmosphere. And then we'll just say that this last one is the pressure that carbon dioxide contributes to the atmosphere. And so when we add together the pressures that each one of these gases contributes, we get the total pressure, which is what you see over here. Okay. The reason that this is important is because we can use this idea to essentially determine the like concentration or pressure of oxygen itself within the air that we're breathing in, and then also within the blood as in terms of how much is actually getting into the bloodstream from the air that we're actually breathing in. Okay, and so because the partial pressure of a gas is kind of what I wrote over here, because it's determined by how much of the gas is actually present, then partial pressures can kind of be used in really much the same way as concentration values in determining also the direction of net diffusion. All right, and so let's talk about this for a second, because I think this is a really important point, is saying that as we have just exhaled CO2, okay, we're getting ready to breathe in some more oxygen. We know that in the atmosphere, there's about close to 20, oops, sorry about that, close to 20% of the atmosphere is oxygen. All right. And so there's said amount of concentration of oxygen in the atmosphere. And so in order for oxygen to flow from atmosphere into our lungs, there of course needs to be a concentration difference or a pressure gradient that allows that. All right. And so inside of our lungs, we need to have less oxygen so that when we go to when we need oxygen, I should say, oxygen will freely flow through diffusion, guys, because remember, diffusion occurs when things flow down their concentration gradients. All right, and so that's really what Dalton's law is all about, is determining which way are these gases going to move. Is it going to move into the lungs? Is it going to move out of the lungs? And then at what pressure is that going to occur? And at what relative amount? So the next law I would like to discuss is Henry's law. Henry's law is going to describe how the pressure of a gas relates to the concentration of that gas in a liquid solution. So excuse me, the reason that this one is actually important to us is because this principle is going to explain to us how the plasma concentration of a gas like oxygen relates to its partial pressure. All right, and so Henry's law is going to say that the concentration of a gas in a solution, so we've got some gas that's dissolving into water here, that is going to depend on two things. It's going to depend on how much gas is out here in the gaseous phase, Okay. And then it's also going to depend on the properties of this gas itself, such as, is it soluble? Is it something that will dissolve into a liquid? Okay. And so, really, what we can think about here is like oxygen, for example. If we're in a situation in which oxygen, the partial pressure of oxygen is pretty low, um, we're going to find that there's less oxygen actually dissolving into the plasma itself. Okay, and that kind of makes sense. Like it should make sense to us theoretically, like in our brains. But one thing to kind of note here is I'm going to give you sort of a twister, a sort of different example. Solubility really matters here. And the best example that I can give you for this is that if we think about like carbon monoxide. Okay. Let's draw on this for a second. All right, let's think carbon monoxide. Carbon monoxide. So carbon monoxide is actually much more soluble than what straight up oxygen is. Okay. And so what this means is that carbon monoxide will preferentially dissolve into the blood over oxygen. Okay. So if we are in a situation where there is both carbon monoxide and oxygen available to us, we will find that there will be more carbon monoxide in the blood over oxygen. And that's all about solubility here. Okay. And so the way that you treat or you can treat carbon monoxide poisoning is that you can actually put somebody in what's called an oxygen chamber. Essentially, it's going to create a space that is nearly 100% oxygen. The atmosphere is nearly 100% oxygen. And by providing a situation right here where the partial pressure of oxygen is now significantly increased because the air that you're breathing in this hyperbaric chamber is, you know, only oxygen essentially. That actually forces oxygen to dissolve into the blood and can then displace the carbon monoxide. All right, and that's one way that you can treat carbon monoxide poisoning is by putting somebody in a hyperbaric oxygen chamber in which the air that they're breathing in is nearly 100% oxygen. It's very different than the air that we breathe in our atmosphere, which again, remember I said contains only about 20% oxygen. So that's how we would apply Henry's law. I just have a couple slides here about applying Boyle's law to inspiration. Now, I already kind of mentioned this, but I have some pictures here that are, I think, somewhat helpful in helping us better understand this. And so inspiration, when we breathe in, this is an active process that ultimately requires both our diaphragm and external intercostals to contract. Okay, and so whenever we actually inhale, it's sort of like taking a bucket and pulling the lid so that it's parallel to, or I guess in line with the top of the bucket. All right, so our ribs normally sit like a bucket whose handle is just sitting along its side, but when we breathe in, that actually lifts the ribs upwards. All right, and it makes it sort of level kind of with the top of the bucket. And what you can see happening then is that that creates extra space laterally, right? So we're actually increasing the volume of the thoracic cavity. And that's kind of what the ribs are doing. Now, the sternum itself, as the ribs are elevating, the sternum is kind of going to, if you guys have ever seen, and I'm sure you have, the water hoses that are at like campsites or are maybe at parks, where if you lift the pump, then the water spigot will activate. And so when you move the pump handle, that's kind of like how the sternum is going to move whenever we inhale. And again, that increases volume anterior posteriorly and not just laterally like what the ribs do. So by ultimately increasing the space within the thoracic cavity because you've physically moved the bones, then this ultimately is going to end up leading to a situation in which the pressure inside the lungs now becomes less than the pressure in the atmosphere. And the um, the kind of result of this is that the air is going to ultimately end up flowing from atmosphere into the lungs. And this is going to continue until the pressures both inside the lungs and in the atmosphere are equal to one another. At that point, it is when we are going to start doing sort of this quiet expiration of and passive process in which our inhalation muscles, our external intercostals and our diaphragm are going to relax. This is going to cause a decrease in the size of the thoracic cavity. This volume decrease causes pressure in the alveoli to build. When the alveolar pressure, excuse me, ends up building, then the lungs are ultimately going to cause a situation in which air is going to flow from inside the lungs out into the atmosphere, because at this point now the atmospheric pressure is lower than what the pressure is inside of the lungs. Okay. And once we get to a situation in which the pressure in the lungs and the pressure in the atmosphere are now equal, expiration stops, and we're essentially going to repeat this process. Now, one important thing to note is that quiet exhalation is passive, right? It does not require muscles in order to occur, but forced expiration is active. And just a reminder, this one uses the oblique and transverse abdominis muscles as well as the internal intercostals muscles. So if we look at this from kind of a big scale of what exactly is going on with pressures and volumes during respiratory cycles, we can see the pressure in the alveoli. All right, so the pressure inside the lungs here. This where it says 760 and this dotted line, that is going to represent atmospheric pressure, because atmospheric pressure doesn't change unless you change geographic locations. And then what we see down here is the intrapleural pressure. And then what we see between them is the transpulmonary pressure. And what we see at the bottom is the volume of the lungs with each respiratory cycle. So let's just think about this. So when we inhale, our lung volume is going to increase. Our alveolar pressure is going to increase. Our intrapleural pressure is going to decrease. Okay. During exhalation, or as our lung volume decreases, the size of our lungs decreases, pressure increases until we reach a point in the lungs themselves in which the alveolar pressure inside the lungs, is equal to atmospheric pressure along this dotted line. Okay, and then we can see we're going to inhale again. And we're going to exhale again, and so on and so forth. So notice Boyle's law here kind of in play, in that when the pressures go up, like here and here, we can see the volume going down. And when the volume goes up, the pressures are trending downwards. Okay, and this is really not showing anything any different. It's just a different graph. If you did not really understand the last one, this is just a different graph for you to look at. So I am going to end this video here. That is all about the gas laws and how they come into play with the respiratory cycle. And I will catch you on the next video about respiratory volumes and how we can use the information that we gather to do different pulmonary tests, pulmonary function tests. So I'll see you then.